Welcome to lecture 4 of design of FIR filters module 3. In this session we will learn cascade form realization of FIR systems. Now we know that the transfer function of FIR systems is m minus 1th order polynomial in Z. So therefore this polynomial can be factored into second order factors. Okay. And before factorizing we need to consider whether the length of the filter capital M, okay, so it is even or odd. Okay. So here also M represents the length of the filter. Okay. So length of the filter, and this M can be even or odd. Okay. So therefore let us consider the factorization and then cascade realization of FIR systems when M is odd. Okay. Now as the transfer function of FIR system is M minus 1th order polynomial. Okay, so it is a M minus 1th order polynomial. Okay, so this polynomial can be factored into second order factors. So that is h of z can be factored into the second order factors h1, h2, h3 like this. So how long it will go? It depends on whether m is even or odd. Okay, so therefore let us see how exactly to implement the cascade form realization by writing the transfer function h of z of the given system as a product of second order factors. So now let us consider the h of z. So we know that h of z is given by bk into z to the power of minus k ranging from 0 to m minus 1. Okay. So now in this cascade realization, the h of z is factored into h1, h2, that is all these are second order polynomials, and this is going to end at h m minus 1 by 2. Okay. So this is for the case when m is odd. When m is odd. Now here h1, h2, h3 etc. up to h m minus 1 by 2 are the individual transfer functions, and each individual transfer can be represented as hk of z. Okay, and each hk of z is nothing but h of, we know that, k naught plus h of k1 into z inverse plus h of k2 into z to the power of minus 2 etc. Okay. So for individual transfer function the difference equation can be now obtained as h of z is equal to yk of z by xk of z. So that is equal to h of k naught plus h of k1 z inverse, okay, plus h of k2 z to the power of minus 2. Okay, so why it is only z to the power of minus 2? It is because all these are, that is h1, h2, h3, these are the factored forms and they are all second order factors. So that's why the maximum power of z can be 2. Okay. Now by taking the inverse z transform on the above equation, so it is possible to obtain the transfer impulse response of the individual stage. Hk of n, okay, is equal to hk naught into xk of n plus h of k1 into xk n minus 1 plus h of k2 into xk of n minus 2. Okay. So now this is what is the impulse response for individual transfer function. Okay. So therefore here k is nothing but represents the transfer function number. It may be 1, 2, 3 up to m minus 1. Okay. So now using these transfer function, that is hk of z, so it is possible to derive the corresponding impulse response. So now we can observe each hk of z, each hk of z when it is written in the time domain form, okay, consists of three samples, h of k naught, h of k1 and h of k2, and also the highest power on the z is 2, indicating that they are second order functions or the second order factors of h of z. Okay. So therefore now this is particularly written for what? M odd condition, that is when the length of the filter is odd condition. Okay. Therefore now the above difference equation is for individual stage or individual transfer function. It may be h1, h2, h3 up to hm minus 1 by 2. Okay. So now in cascade realization, the direct form structures are now drawn for these individual difference equations. Okay, and then they are cascaded. That is to obtain the overall cascade realization. So first we need to obtain what is h1 of z, h2 of z, h3 of z, etc. And then each transfer function has to be converted into its difference equation. Using that you can draw the direct form, okay, and those direct forms are cascaded to obtain the complete cascade form realization for the given system. Okay. So therefore now in the block diagram form we can represent the cascade realization as shown. So basically what we have is the input x of n. Okay. Now this input x of n, so it is nothing but actually it is x1 of n as it is entering into the first block. So therefore when it passes through the first cascade, that is the first factor, that is h1 of z, it generates y1 of n output. Okay. So now whatever y1 of n output is there, so this acts as a second input, that is x2 of n for the next stage. So this is h2 of z. h2 of z output is nothing but y2 of n, so which in turn acts like a x3 of n input to the next stage, that is h3 of z, h3 of z. Okay. So therefore this process continues and we have the last stage, that is hk of z generating the final output y of n. Okay. And it receives y k minus of n as the input, which is nothing but xk of n, xk of n. Okay. So this is what is the block diagram version, and in this, within this particular block diagram, whatever individual transfer functions are there, h1 of z, h2 of z, okay, so we can draw here one basic second order section. So these are the individual sections. Okay. So for these individual sections, that is h1 section, h2 section, we are drawing the direct form realization. So therefore in this is figure A. So in figure B we can draw one basic second order section, and it looks like this. So suppose xk of n is the input, then as individual sections are nothing but second order sections, so we have z inverse and z inverse because it has to generate two delays, and then first coefficient, that is b k naught, and after one delay the delayed signal is multiplied by b k1, and then one more time the signal is delayed and this will be added with the previous result. At the same time the delayed signal is multiplied by bkx2, and here we are going to get yk of n, yk of n. Okay. So this figure B, so this is nothing but the basic second order section it is. Okay. So this actually represents what? It is a structure for individual individual transfer function. Okay. So the same sections are finally cascaded to obtain the overall realization for the given system. Okay, so therefore in the cascade realization, it is possible because it is we can split h of z, or we can factorize h of z as the product of individual transfer functions, and these h1, h2, h3 etc., they are all the second order factors. Okay, so in other words, we can say that the system transfer function h of z can be expressed as the product of second order factors. Okay, and the product of these second order factors, the general equation is like this: h of z equal to summation k equal to 0 to m minus 1 bk z to the power of minus k, where m represents length of filter. Okay, now that can be even or odd. So now we are considering the first condition, that is when m is equal to odd. Okay, so when m is odd, what is the further process? That is, factorize h of z into h1, h2, h3 up to hk, and then whatever the individual transfer functions we get, that is, which are all nothing but the second order factors. So for them it is possible to further derive their corresponding difference equations like this. Okay, so now these difference equations, they have either z raised to minus 1, z raised to minus 2, that's all. This is because the reason that they are all the second order factors. Now the individual difference equations can be further implemented using direct form structures. Now in this particular slide, the block diagram representation of cascade architecture is shown, where h1, h2, h3 up to hk of z, they are the individual second order factors. And now figure B shows a basic second order section. Okay, now similar sections are cascaded. So only thing is their coefficients may be different, that's all. Further, structure wise, the basic second order section is common. Okay, so these sections are cascaded in order to obtain the overall cascade form realization for the given system. Okay, so let us make it clear by considering one example. See here, it is the problem given is like this. Now using cascade structure, realize a FIR filter representation for the following transfer function. So a transfer function is given like this. So h of z is equal to 1 plus 1 by 2 z raised to minus 1 plus z to the power of minus 2, this into 1 plus 1 by 4 z inverse plus z raised to minus 2. Okay, now this is a given transfer function. So for this, realize using cascade. Cascade structure. Realize using cascade structure, or obtain cascade realization for the given transfer function h of z. Okay. So now in this problem, already the factored version itself is given. Okay, so h of z is nothing but the product of two second order factors it is. So therefore readily you can write here what is h1 of z. Okay, so h1 of z is nothing but 1 plus 1 by 2 z inverse plus z to the power of minus 2. Okay, and h2 of z is equal to 1 plus 1 by 4 z inverse plus z to the power of minus 2. Okay, so therefore now for the cascade structures, so how do we write? H of z, that is the overall system transfer function, is equal to h1 of z into h2 of z. Okay, so therefore now we will realize h1 of z and h2 of z using the direct form structures, and then we will obtain their cascade. So therefore let us individually take the transfer functions. So now consider first h1 of z. So h1 of z can be written as y1 of z by x1 of z, because we have to obtain what? The convolution sum equation, okay, in the time domain, and that can be put into the direct form structure. That's why. So this is equal to, from the given problem, its value is 1 plus 1 by 2 z inverse plus z to the power of minus 2. Okay. So now my intention is to obtain y of n. So therefore first I will write on the LHS y of z. By cross multiplying, I have x1 of z plus 1 by 2 into z inverse x1 of z plus z raised to minus 2 into x1 of z. So by taking IZT on the above equation, so I am going to obtain y1 of n. So y1 of n is equal to, so x1 of n plus 1 by 2 into x of n minus 1 plus it is x of n minus 2. Okay. So z inverse z raised to minus 2 into x1 of z is nothing but, its iz is nothing but x of n minus 2. So here you can write the suffix as x1 because this is the first part, and for the first transfer function we will consider input as x1. For the second section we will consider input as x2 according to the standard block diagram that we have drawn. Yeah. So now once we obtain y1 of n, okay, so this is the difference equation for the what the first section in the cascade. Okay, so now this is one important result. Now similarly take the h2 of z. Okay, so what was h2 of z? 1 plus 1 by 4 z inverse plus z raised to minus 2. So following the same procedure, you can see that y2 of n for this will be x2 of n plus 1 by 4 into x2 of n minus 1 plus x2 of n minus 2. So this is the difference equation for second stage in the cascade. Okay. Why it is x2? Because previously we had written one block diagram, that is whatever our input is there, first x of n input, when it is passing through h1 section, so we will consider it as x1 of n, and the output from the first stage we have considered it as y1 of n. Okay. Similarly this y1 of n, okay, it actually passes through h2 section, and so we consider x2 of n as the input. So therefore y1 of n serves as a input x2 of n for the second stage, and the second stage output will be y2 of n, and as there are only two stages in this particular problem, so y2 of n itself will be equal to y of n, that is the final output y of n. Okay, so that's why while writing the first stage difference equation, all our inputs are represented by the suffix 1 for the x, that is x1 of n, and while writing the difference equations for the second stage, so the suffix for x will be 2. Okay, so x2 of n, x2 of n minus 1, x2 of n minus 2. So now once we obtain the individual difference equations for the two stages, so now we can draw their cascaded structures. So now as I told you, h1 of z and h2 of z, so these two are individually realized by direct form structures only. So only thing is we need to cascade those two direct form structures. So therefore the cascade realization for the given problem is like this. Now first we'll write the first stage, that is x1 of n is the input for that stage, and you just keep in mind x1. Okay, so in this equation what we have, x1 of n minus 1, then x1 of n minus 2. So two delays are there. So therefore, so here itself we will mention the two delays, z inverse and one more delay, z inverse. Okay, so because after this delay I am going to get here x1 of n minus 1. After another z inverse, here I am going to get x1 of n minus 2. Okay. Now the delayed sample, what we have the equation, x1 of n minus 1 is multiplied by 1 by 2 and x1 of n minus 2 is multiplied by here 1. Okay. So therefore here x1 of n minus 1 will be multiplied by the coefficient 1 by 2, and similarly here it will be x1 of n minus 2 will be multiplied by 1. Okay, now all are added. So therefore the addition is shown like this, and finally these two delayed samples are added with the incoming signal x1 of n, x1 of n. Okay, now here we are going to get y1 of n as the output from the first stage. Okay, so therefore now I will mark this particular stage as the first stage, which is going to generate y1 of n. So this entire part will be representing h1 of z, h1 of z. Okay. So similarly our y1 of n now acts as actually x2 of n input for the second stage implementation. So even the second stage also, what is the difference equation? y2 of n is nothing but x2 of n plus 1 by 4 into x2 of n minus 1 and 1 into x2 n minus 2. So therefore here also two delay elements are there. First delay multiplied by 1 by 4, second delay multiplied by 1. So therefore drawing the structure, direct form structure in the same method, I have Z inverse and Z inverse. Then this is actually multiplied by 1 by 4 according to the problem. This is multiplied by 1. Okay. Now this is added, and here this signal will be added with the x2 of n, x2 of n, and finally this is going to generate y of n output. So therefore here also we can show that this is the second stage. And this is h2 of z. This is h2 of z. So now this itself is the cascade. Okay. So the output from the first stage, first of all h of z. Okay. So first of all h of z is split into two factors, h1 of z and h2 of z. Both are second order factors. Okay. So this is also second order and this is second order. So why it is possible to split into second order only? It is because m is odd in this case. M is odd. Okay. So when m is even, we will take in the next section. So when m is odd, actually we are getting m minus 1 as even. M minus 1 as even. Okay. So therefore it is possible to get the second order factors. So now we have derived the difference equation individually for h1 as well as h2, and now we have realized them by direct form structures only individually, but they are cascaded. Okay, so that's why this entire realization is called as cascade realization of the FIR system, and the final output y of n is available at the end of second stage. Okay. Now this is the solution for the first problem, that is where already h of z was factored and both factors were second order, and also satisfying the condition that m is odd. So how did you determine here that m is odd? So here itself you can compute that, and also we can calculate what is m also in this problem. So when you multiply z raised to minus 2 into z raised to minus 2, the highest power what I am getting is z to the power of minus 4. Okay, so as it is z to the power of minus 4, so we know that it is the h of z is a m minus 1 polynomial. Okay, so therefore why it is 4? Because m minus 1 is equal to 4. Therefore obviously m should be equal to 5. So therefore the given problem is for m equal to 5. Okay. Next. Next we will take another condition where m is even, that is filter length is even. When m is even, when m is even, you can just observe that whatever summation we have, k equal to 0 m minus 1. Okay, so now this m minus 1 becomes odd. That is actually this m minus 1 becomes odd. For example, if m is equal to 4, then it will be summation k equal to 0 to 3. Okay. So therefore now in that case, okay, h of z will have, okay, so h of z will have one first order factor and remaining m minus 2 second order factors. Okay. So this is what is the solution proposed when m is even. Okay. So therefore whenever the filter length m is even, the h of z, the system transfer function h of z is split like this. Okay. So it will have one factor, that is the first order factor, and remaining m minus 2 by 2 second order factors. Okay. And what will be the format of the cascade? The cascade structure will have one first order section. Okay. So the cascade structure will have one first order structure and m minus 2 by 2 second order sections. Okay. So the entire cascade structure now will have two parts, that is at the beginning. Okay. So it will have one first order section and remaining sections will be m minus 2 by 2 number of second order sections. Okay. So therefore now let us take one example to draw the cascade structure in this condition, that is when m is even. Okay. Now the transfer function of a system is given by h of z is equal to 1 minus 5 by 4 z inverse plus 3 by 4 z raised to minus 2 minus 1 by 8 z raised to minus 3. Okay. So now realize this system by cascade structure. Okay. So in the solution, we will write first the given h of z in the form. So h of z will be equal to y of z by x of z, and this will be equal to 1 minus 5 by 4 z inverse plus 3 by 4 z raised to minus 2 minus 1 by 8 z raised to minus 3. Okay. So therefore now obviously here we see that the highest power is 3 here. 3. So therefore m minus 1 is equal to 3. So therefore m is equal to 4 in this case. Okay. So therefore now whenever you are going to draw the cascade form realization, how we have to split h of z now. Okay. So h of z can have one first order Okay, so one first order section and m minus 2 by 2. Okay, so m minus 2 by 2, it means in this case what is m? 4 minus 2 by 2, that is 2 by 2 1. Okay, so one second order section, it will have one second order section. Okay, now the number of second order sections may vary depending on the m value here, but as m is equal to 4 in this problem, okay, so this m minus 2 by 2 we are getting as 1. So therefore for the given problem we have one first order section and one second order section. So therefore now we need to factorize, okay, h of z into, we need to factorize h of z into h1 of z into h2 of z. Okay, so therefore for the given problem, h of z factors will be 1 minus 1 by 4 z inverse into 1 minus z inverse plus 1 by 2 z raised to minus 2. Okay, so now these are the factors, and here itself we can see that, this is the first order, and this is nothing but the second order factor, it is. Okay, so now this is h1 of z and this is h2 of z. So that's why when you perform the cascade realization, the first section will contain this first order part or the first order section. So next the second order section will be following. Okay. Therefore now let us derive the difference equations so that we can draw the direct form structures first, and later we can cascade h1 and h2 parts. So therefore so from the given problem, h1 of z is nothing but 1 minus 1 by 4 z inverse. So this is nothing but equal to y of z by x of z. You can just cross multiply and take the inverse z transform. So y1 of z will be equal to, so x1 of z. Now I am indicating inputs as x1 and x2 for the two parts. Minus 1 by 4 z inverse x1 of z. So by taking the inverse z transform, now I am getting the y1 of, that is the first output from the first stage or the first section. So this will be equal to x1 of n minus 1 by 4 x1 of n minus 1. So this is the output for the first stage. So this is nothing but the first order section. Okay, now remaining all sections will be second orders only. So next go to the second part, that is h2 of z part. Okay, so h2 of z is 1 minus z inverse plus 1 by 2 z to the power of minus 2. So again write in the form of y2 of z by x2 of z. So performing cross multiplication and taking IZT will give us the final output. So here of course it is y2 of n, but y2 itself is a final output y of n. So therefore directly I am writing y of n is nothing but x2 of n minus x2 of n minus 1 plus 1 by 2 x2 of n minus 2. Okay. So now this is the second stage output as well as the final output y of n. Okay. Now why it is x2 here? Because whatever y1 of n is there, so this acts as a input x2 of n for the second stage. So that's why we are able to write the second stage difference equation like this. So now as we have y1 of n as well as y2 of n, which is nothing but the final output y of n only, we can draw the cascade realizations. Okay, so the realization is like this. First stage, it is a first order stage, so therefore it is a very simple equation, x1 of n minus 1 by 4 x1 of n minus 1. So therefore there is only one delay in this, so the delay will be z inverse, and this will be added, and for the just go back here, 1 by 4 is multiplied with x1 n minus 1. So therefore here minus 1 by 4. The delayed signal will be multiplied by minus 1 by 4, and the output, that is y1, it is actually feeding as a input for the second stage. Okay. In the second stage, the equation what we have, x2 of n minus 1 and x2 of n minus 2. Okay, so therefore I am drawing the two delays, z inverse and then z inverse. So here actually what I am getting the signal as x2 of n. So this point represents now x2 of n minus 1. The second point here, this represents, okay, this is x2 of n minus 1 point, and here it is x2 of n minus 2 point. So x2 of n minus 1 is having the multiplication factor minus 1, and this will be going to adder. Similarly, x2 of n minus 2 is having the multiplication factor as 1 by 2, and this will go to the adder. Okay, so now this signal will be added with the x2. You can see this, the first term x2. Okay, so this is going to generate the final output y of n. Okay, so therefore now we have the two sections. This is the first section. Now this is the second section in the cascade. Now this implements h1 of z, and this implements h2 of z. Okay, so now this is how for both the even condition as well as odd condition, the cascade realizations for the given transfer functions are obtained. Thank you.